So for lecture today, we're going to start Chapter 7. Chapter 7, we're going to be dealing with impact. Now, when we're talking about impact, we're really talking about dynamic loading. So in order to really get into dynamic loading, we want to go back a little ways to take a look at our content of our statics course and our dynamics course and really look at the difference. So if we think back to statics, we're talking about a constant, a slow ramp or pseudo-static style of loading. Whereas in our dynamics course, we're looking at exactly what we need to talk about now, impact, which is a suddenly applied load. So this is something we want to consider when we're looking at these problems, is what type of loading do we have, and if we're dealing with impact, it's going to be a dynamic load. Now when we're talking about dynamic loading, one thing that we do want to know is materials are going to show rate-dependent behavior. So depending on which rate we're loading these with under a dynamic load, we're going to see a change in the increasing strain rate. So if we look at our stress-strain diagram down here, as we change the load, we're going to see differences in the strain rate based upon the actual loading rate. We're now going to take a look at example problem 7.1. In this problem, we have a car that skidded off an icy road and then became stuck in deep snow at the road shoulder. Another car with a known mass of 1,400 kilograms attempted to jerk the stuck vehicle back into the road using a 5-meter steel tow cable with a known stiffness given to us as K is equal to 5,000 newtons per millimeter. The traction available to the rescue car prevented it from exerting any significant force on the cable. Now, with the aid of a push from bystanders, the rescue car was able to back against the stuck car and then go forward and reach a speed of 4 kilometers per hour at the instant the cable became taut. If the cable is attached rigidly to the center of mass of each car, estimate the maximum impact force that can be developed in the cable and the resulting cable elongation. So now looking down at the schematic here, we can see this is our stuck car over here. Then we take a look on the right. Here's the car that came along with a mass of 1,400 kilograms and attempted to jerk the other stuck car out of the snow. Here's our cable down here, our rope. We have a known K value of 5,000 newtons per millimeter. We have a known length of 5 meters. And when the cable becomes taut, we then have a velocity given to us in the problem statement is 4 kilometers per hour. Now that we've had a chance to go through the given problem statement schematic for this problem, the next step is to write things out in the correct format, same format that we've used for all the homeworks and exams before. So the first thing that we want to do is figure out, what do they tell us? What are we given in this problem statement and the given schematic? What information do we have? And again, we want to write out several different things. We want to write out the variable, the value, the units, and how it actually relates to our problem in words. So what we do have for this problem that we know is, we know that the mass of the car is given to us as 1,400 kilograms, and this is the rescue car mass. L is given to us as 5 meters, which is the length of the cable. K is given to us as 5,000 newtons per millimeter, which is the cable stiffness. And V is the velocity or speed of the car as 4 kilometers per hour. Now, the first thing I want to note here right off the beginning is we have several different units that don't correspond with each other. So we can see we have meters and millimeters, and then we have kilometers, and we also have per hour up here. So we may want to convert things either all to meters or all the millimeters at some point. But right now, I haven't really made a decision as to which way I want to go with this, so I'm going to leave them up here just as they were given to us in the problem statement, and later on I'll convert these off to the side, all to the same units, to make our lives a little bit easier as we plug in to the governing equations for this problem. The next thing that we do down here is we redraw the given diagram. So I simplified it down just a little bit. We have the rescue car on the right, we have the car that's being pulled out over here on the left. There's our cable in between the two. We know the length of the cable is given to us as 5 meters. We have the spring constant is 5,000 newtons per millimeter. Then over here, when it's taut, when the cable is taut, we have a velocity of 4 kilometers per hour. And we know the mass of this rescue car is 1,400 kilograms. So now that I have the information, the next step is to figure out what are they asking us to solve for on this problem. So what they want us to find is the minimum impact force. So we're looking for a force here with this here, and the resulting elongation that develops in the cable. So we're interested in the cable itself. We want two different things with that cable. So two parts to our solution here. One to solve for this impact force, and the next to solve for the resulting elongation of that cable. So we want to make sure we label things correctly. So my impact force here is my elastic force. I'm calling it F sub E here. And we'll have a delta for our elongation that we'll use for our symbol for this here. Now, the next thing we want to do is figure out, okay, what are the simplifications? What assumptions are going to make for this problem in order to make it a little bit easier for us to solve? So the main assumptions we have 5 of them here. So the first assumption we're making is that the cable is attached rigidly to both cars. 2, we want to ignore the mass of this cable. 3, we want to neglect any stress concentrations. 4, we're going to ignore damping due to internal friction within the cable. And lastly, the rope responds to the impact elastically. So these are the assumptions we're going to make from this, from our given information, our schematic, what we're looking for in our assumptions. Now we're going to start our solution. So in order to start our solution for this problem, what we want to do is take a look at equation 7.4a on page 196 of our textbook. So here is our governing general equation that we're going to pull from 7.4a. This is saying that our elastic force, which we've determined to be F sub E for our variable name, is equal to W times the square root of V squared over G times delta. Now, what these are, we need to define clearly for this specific problem. So we have our weight, velocity, gravitational constant, and deflection in our general equation. Now for our specific problem, I rewrite all my known values down here for everything we're going to need for this. And one thing I notice is we don't have a weight, but we know that weight is mass times the acceleration due to gravity, so I've clearly wrote out all these variables down here. So V is given to us, our velocity is given to us in the problem statement as 4 kilometers per hour. I don't want to make that conversion right now to meters per second, so 4 kilometers per hour converts to 1.11 meters per second, and this is that velocity of the rescue car once the rope or cable is taut. Now G is my acceleration due to gravity. This is 9.81 meters per second squared. So this is why I chose to go to meters per second here, because I know my gravitational constant is in meters per second squared here. Just want to make sure everything is in the right units so we can do our unit analysis and make sure everything checks out within our equations. Next we see we have our W for weight. Weight is equal to mass times the acceleration due to gravity. So I've left it as this here. We'll plug these in later. But we know that mass is given to us. So this is the mass of the rescue car of 1,400 kilograms. Then we have our spring constant down here for the cable. And our spring constant is given to us as 5,000 in the units of newtons per millimeter. Now everything else I've seen has been in meters, so I want to convert this to meters here. So this is equal to 5 million newtons per meters, and this is going to be our spring constant K. The last variable we have here is our delta, or our deflection or elongation here. This is given from equation 7.4f in our textbook, and this is saying that this is equal to W over our K value there, which we have both of those now up here, where W is in terms of our M and our G. So the next things we want to do is for our W and for our deflection here, delta, we want to go down through and plug in our values for these here and get out some numerical values and get them in terms of our other variable names that we have. So our weight, again, is equal to mass times the acceleration due to gravity. So our mass is 1,400 kilograms, and our acceleration due to gravity is 9.81 meters per second squared. So this, when I multiply these two together, is 13,734 newtons. Now it's newtons because we have kilogram meters per second squared. Kilograms meters per second squared is newtons. So our weight force is 13,734 newtons. Do the same thing now for deflection. Going back to equation 7.4f, we know the deflection is equal to weight divided by our spring constant here, where now we've just solved for our weight in the equation above, 13,734 newtons, divided by, now I'm doing my K value in terms of newtons per meter. So I have newtons up here, newtons there, and I want to have it left in meters. So what I want to do is divide newtons divided by newtons per meter to end up with meters in the end. So I divide this by our 5 million newtons per meter, and I end up with 0.00275 meters for the deflection or the elongation of that cable there. So now I can take this value here and I can plug it back into 7.4a at the top of the page here. So I have all of these different values. I have my delta, I have my g, I have my velocity, I have my weight, I have everything I need to plug back into 7.4a. So that's the next step I'm going to do, is go back to my general equation, 7.4a, right here. So there's my general equation for 7.4a. So my elastic force F sub E is equal to weight times the square root of velocity squared divided by the acceleration due to gravity times our deflection here. Plug in our known values now, and I leave my units in as well so I can double check. So our weight is in units of newtons, 13,734 newtons. And over here on the right side under the radical, we have our velocity of 1.1 meters per second squared. Again, I went into meters per second for this to correspond to the other units. Gravitational acceleration is 9.8 meters per second squared. And we have now our deflection that we just solved for in meters here. So we can look at all these, do the unit analysis. Our units end up canceling out on the right. So this becomes unitless over here. Do out our math there, square root of 45.83 times our weight force in newtons there. Square root of 45.83 is roughly 6.77 times our weight force there of 13,734 newtons. Do out the math here, and what we end up with is that our elastic force here is 92,984 newtons, or 92.9 kilonewtons. So therefore, the max impact force is 6.77 times the gravity weight of the car. So from there, the next thing that they'd asked us to solve for in the problem, part 2, was for the cable elongation. So in order to solve for this elongation, we can go back to the same relationship we've seen before for our delta function here, where our delta is equal to, in this case, F over our K, where F is this max impact force, the maximum impact force, divided by the spring constant. So we plug in our known values. We've just solved for this maximum impact force is 92.9 kilonewtons. And we know that our K value here, if we go down in terms of meters, is 5 million newtons per meter. So again, make sure we understand we're in kilonewtons and newtons and plug in correctly into our calculator before we solve this. We plug those values in and we find out that our elongation of the cable is equal to 0.01859 meters, or if we convert this down to millimeters, the elongation is 18.6 millimeters in the cable. For the next example, we're going to take a look at sample problem 7.1, axial impact, importance of section uniformity. So the figure here shows two round rods that are both subjected to the same tensile impact. How do the elastic energy absorbing capacities compare? So we have these two round rods with different geometries. And we can see this one is uniform all the way down with a diameter of d. This one changes about halfway down here, L over 2. The top half is twice the diameter of the bottom half. This bottom half is the same in part B as it is in part A, but the top half, the upper half of part B, is twice the diameter of the rod in part A. So we want to take a look here. Now we have an area of equal to pi d squared over 4. We have a total length L. Again, here the total length is still L. This divides L over 2 and L over 2 here. And one thing we do want to note is that we're going to neglect the stress concentration and use our yield strength SY as an approximation of the elastic limit. And that's going to become important when we choose our governing equation. We need to sub in this yield strength in place of our stress concentration. Now that we've looked through the given problem statement and schematic for this, we want to go ahead and write this in the correct format, again, similar to the homework and exam problems we've done before. Write out everything that's given to us, simplify down our given diagram, find out what they're asking us to solve for, and write out all of our assumptions we're going to make to simplify this problem. So, for your first part of this, what is given in this? Well, we have two round rods of given geometries. We know what the geometries are. It's shown for both A and B in the schematic below. These are going to be subjected to a tensile impact. So we redraw these out here. Not too much different from what we saw in the actual given schematic. It's pretty simplified to begin with, but I have part A and part B for rod A and rod B. And again, we look at geometries here. We have the total length L on both of them. Uniform diameter all the way down through for A. An area is equal to A of A equals pi d squared over 2. And then for part B, the top half is going to be twice the diameter of that of the lower half. And we have the same lower half diameter d as we do in part A. So we have this right here now given to us as our schematic. We understand the difference between rod A and rod B. So what are they asking us to solve for? Well, in this problem, they ask us to compare the elastic energy absorbing capacities of the two rods. So that means what we're going to want to do is solve for this elastic energy absorbing capacity for both A and for B, and then compare them and see how the two of them compare to each other. So in order to do this, we're going to have to make several different assumptions. So there's 6 different assumptions we're going to make to simplify down the solution to this problem. Assumption number 1, we're going to assume that the mass of each rod is negligible. So we're ignoring the mass of these rods. 2, deflections within each impacting mass itself are negligible. 3, friction damping is going to be negligible as well. 4, each rod responds to the impact elastically. 5, the impact load is applied concentrically. And 6, the stress concentration can then be neglected. So now we have these 6 assumptions. We know what they're given in the problem. We know the geometries between A and B, and we know what we're looking to solve for. So the next step in this here will be to go through and start our solution and find our key governing equations. So now we're going to take a look at our solution. So the first thing we want to do when we're solving this out is to calculate this elastic capacity for A. So we need to do this for both rod A and rod B for this problem, but let's solve for each of these separately, and let's just take a look at them one at a time, starting with rod A. We recall that is part A is going to have a uniform diameter the entire way. So for this here, the first thing we want to do is come up with our governing equation. And this governing equation comes from equation 7.5a on page 197 of our textbooks. So this says that U is equal to sigma squared times V divided by 2E. Now, for each of these variables, we know that U is the stored elastic energy, sigma is the stress, V is the volume, E is the modulus of elasticity, and we're also going to need our S of Y, which is our yield strength. Because in our problem, it tells us that sigma is equal to S of Y, or our yield strength for this problem here. So we're going to want to plug this relationship back into the general form of equation 7.5a in order to solve for our specific problem for part A. So we do this here. We say, okay, now our stored elastic energy use of A for rod A in the beginning part here is equal to, instead of sigma squared, we have S of Y, or yield strength squared, times V, which again is our volume, divided by 2 times E, which again is our modulus of elasticity. So this now gives us a specific equation that solves for the stored elastic energy in rod A of the uniform diameter. So now that we've done this for part A, we want to do the same thing for rod B. So with rod B, we have a couple things that we need to know before we start our solution. So what we know about rod B is that the energy absorbed by the upper and lower halves, based on the geometry, must be determined separately. So we have a different top diameter than the bottom diameter. The top diameter is twice that of the bottom diameter. So the smaller lower half is going to be the critical one. It can be brought to a stress of S of Y, our yield strength there, and its volume is going to then be half of V, or V over 2, where V is the volume of the full length of the rod. So those are a couple things to note there. So now that we know we need to deal with these each separately, let's take a look at the lower half first, because this is going to be determined to be the critical half of this rod. So the energy capacity of the lower half, I'm going to come up with a variable name for this, so our energy capacity U. So this is part B, lower half. So U sub BL is what I'm using for my notation here. We go back to that same governing equation, equation 7.5. And again, I write this out in general form first. So U is equal to sigma squared V divided by 2E, where again, for our specific problem, recall that sigma is going to be replaced with our yield strength S sub y. So we plug that back in. U is then equal to S sub y squared times V divided by 2E. So volume, modulus of elasticity, yield strength. So again, for this lower half of part B, I use this notation here, U sub BL, the lower half of part B. I have this equation here, but now we also have this relationship here for volume from up above, based on our geometry there. So this U sub BL is equal to S sub y squared times V over 2 divided by 2E. I pull out a 1/2 here, and I end up with SY squared V over 2E. We recall this relationship here is exactly what we solved for U sub A, for part A with uniform diameter. So therefore, the lower portion of part B is going to be 1/2 of what we solved for on U sub A. So we write that out here because they asked us to compare the capacities here. So the capacity here is 1/2 of what we solved for in part A. Now this is just for the lower. All we solve for right now is for the lower half. So now we still need to solve for the upper half, and recall that upper half has twice the diameter of that of the lower half. So now that we've finished the solution for the lower half of part B, we want to take a look at the upper half of part B. And if you recall, for the upper half of part B, the top diameter of the rod is twice that of the lower diameter of the rod in part B. So the same force is through the entire full length of the rod, but the upper half is going to have 4 times the area of the lower half. If we take a look at our geometries and our equation for area, we can prove for ourselves this is 4 times the area of the lower half. It's also going to have 4 times the volume and only 1/4 the stress. So again, we can go back, take a look at our geometries and those equations and prove to ourselves that again, 4 times the area, 4 times the volume, and only 1/4 the stress. So based on that, now we can go through and calculate the energy capacity of the upper half of part B. So again, I'm using this variable name over here for the capacity for part B in the upper half. So U, the subscripts BU for part B, upper half. Now we can go back to our same general equation, 7.5a in our textbook, where we have that U is equal to sigma squared V over 2E, where for our specific problem, sigma is equal to S sub Y. So if our sigma is equal to S sub Y, then we can plug this back in and get this relationship over here, where U is equal to S sub Y squared times V over 2E, where again V is our volume, E is our modulus of elasticity, and S sub Y is our yield strength. So now based on these ratios up here that we found up top, based off our geometries, we can plug back into this general equation here, where now S sub Y becomes S sub Y over 4. So we plug that back in for our S sub Y there, for again for 1/4 of the stress. Then over here our volume, if we have V over 2 in the original one for the lower half of part B, 4 times that would be 2V, all over 2E. I can take a look at all of these numbers here, pull them out, reduce and simplify, so I can say, okay, S sub Y over 4 squared is the same as S sub Y squared over 16. I have a 2 and a 16 here, which comes down to a 1/8. So we now have 1/8 SY squared V over 2E over here, which, if we recall, this is our U sub A. So this would be U sub BU, which is the capacity for part B upper, is equal to 1/8 of U sub A. And that's what it asked us to do, was compare those together. So U sub BU is equal to 1/8 that of U sub A. Now, what we need to think about is this is for the upper and lower portions separately for U sub B. We need to combine these together to really compare part A and part B. So that's what we do here now. To get the total energy capacity for rod B is going to be U sub B is equal to U sub B lower plus U sub B upper. So we solve for both of these. U sub B lower is 1/2 U sub A, and U sub B upper is 1/8 U sub A. As we compared those two, we've already done the comparisons back to U sub A, so that makes our life nice and easy here. We can make common denominators for this, so we have 4/8 U sub A plus 1/8 U sub A to get the total energy capacity for rod B. So therefore rod B is going to be 5/8 times that of use of A. So this is our final answer here, comparing the capacities of part rod B and the part for rod A.